Of all the creatures that once inhabited our planet, large arthropods are viewed with macabre fascination as eerie, almost otherworldly beings, from gargantuan dragonflies to colossal sea scorpions. The prospect of these chitinous creatures achieving such dimensions seems unnatural, as though their existence violates some fundamental law of nature. Nevertheless, during the mid to late Paleozoic, arthropods attained sizes inconceivable among their modern descendants. Yet, even in a world of titanic bugs, Arthropleura stands out as the largest known arthropod that ever existed. Between 345 million and 290 million years ago, these creatures, more than 2.6 meters or 8.5 feet long, crawled across what is today North America and Europe, leaving tread-like tracks in their wake. Since its discovery in 1854, Arthropleura is one of the few extinct arthropods to be regularly featured in popular media, appearing in documentaries such as Walking with Monsters, First Life, and Life on Our Planet, and the 2007 television series Primeval. The creature has also received attention as the subject of over 100 scientific papers. Arthropleura's checkered taxonomic history features fierce debates about its affinities. Jordan and von Meyer described the first species as a decapod crustacean. Salter thought it was a type of Eurypterid. Waterlot interpreted it as a distinct biramous arthropod equivalent in rank to Trilobita, while Manton considered Arthropleura a unique type of uniramian arthropod, outside of either myriapods or insects, and Rolfe and Ingham assigned the genus to its own distinct group within myriapods. Most recently, Wilson and Scheer suggested that Arthropleura was a crown group millipede. The giant arthropod has perplexed paleontologists for decades. Arthropleura's body had characteristics like a millipede, but without the head, scientists couldn't understand the creature's relationship to modern arthropods like millipedes and centipedes. While these two modern creatures may look similar, they actually diverged about 440 million years ago, way before Arthropleura came around. Paleontologists wondered if Arthropleura was a member of the millipede group or the centipede group. Arthropleura's family tree controversy features fierce debates about its affinities, but with the discovery of an intact head, the mystery of Arthropleura now appears solved. The CT scans virtually uncovered the fossilized head of two juvenile Arthropleura discovered within rock in the Montclair-la-Mine La Gestata fossil site in France. These CT scans revealed unique stalked eyes jutting from the side of the head, gently curved antennae, and small centipede-like mandibles. Together, these traits made up a confusing amalgamation of centipede and millipede-like characteristics. Based on anatomical features, paleontologists ultimately grouped Arthropleura as most closely related to the millipede family. However, these stalked eyeballs have never been seen in the millipede or centipede families. Arthropleura has been widely considered terrestrial, but eye stalks are typically found in semi-aquatic or fully aquatic animals, like crustaceans. Because the head belongs to a juvenile, the explanation might lie in the animal's life stage. As juveniles, Arthropleura may have spent more time in the water before losing the stalked eyes in adulthood. The stalked eyes remain a big mystery, because we don't really know how to explain this. Even if these specimens did have an amphibious habit, this does not mean that Arthropleura spent its entire life lurking around lakes and rivers. The specimens described by Le Heritier are juveniles and as such afford a unique view into the ontogeny of this gigantic arthropod. The recognition of juvenile material has important ramifications for the delineation of species within the genus, as a number of previously identified Arthropleurae species bear ornamentation closely resembling that of the juveniles and may themselves be juveniles. This is an important conclusion in and of itself, one likely to have major implications for our understanding of the species' diversity and evolutionary history of Arthropleura, It is also possible that juveniles and adults inhabited slightly different environments and that these stalked eyes may have been a trait lost in adults. The head of Arthropleura combines features of millipede and centipede. For example, the antennas are really millipede-like, while the mandibles are centipede-like. And so this is quite, I would say, striking. This lends new credibility to a controversial theory that millipedes and centipedes are more closely related than previously believed, with Arthropleura as a shared ancestor. Based on its mouthparts and a body built for slow locomotion, the researchers suspect Arthropleura was a detritivore like modern millipedes, feeding on decaying plants, rather than a predator like centipedes. You can think of it like an elephant or a long-necked dinosaur, a big animal spending most of its time eating. Alongside centipedes and millipedes, two other groups of myriapods exist today: pauropods and pseudocentipedes, or garden centipedes. These two diminutive groups have long been considered to have close affinities to millipedes based on anatomical data and form a group called Progoniata, with centipedes distantly related to millipedes. This classic view was recently challenged by molecular data, which suggested a close relationship between centipedes and millipedes, forming a group called Pectinopoda, to the exclusion of pauropods and pseudocentipedes, which resolved in their own group called Edaphopoda. Gigantism during the Carboniferous. One of the most important factors that contributed to the gigantism of Arthropleura during the Carboniferous period was the significantly elevated oxygen levels in the Earth's atmosphere. Atmospheric oxygen levels were as high as 35% compared to the 21% we experience today. Arthropods, including Arthropleura, rely on a passive system of oxygen diffusion through spiracles and trachea, which is less efficient than the lungs of vertebrates. Higher oxygen concentrations allow them to take in enough oxygen to support larger bodies, as diffusion would have been more efficient. This was particularly critical because larger arthropods with more body mass require a greater intake of oxygen to supply their cells with the energy they need. This oxygen-rich environment was essential in overcoming the limitations imposed by their respiratory systems and contributed significantly to the gigantism of many species during this time. During the early Carboniferous period, terrestrial ecosystems were still dominated by invertebrates like Arthropleura. At that point in evolutionary history, vertebrates had only recently begun to colonize land, and large terrestrial predators such as early amphibians and reptiles were not yet prevalent. This lack of large vertebrate predators likely allowed Arthropleura and other invertebrates to grow without the constant pressure of predation. With fewer large terrestrial animals to compete with for resources and fewer threats to avoid, Arthropleura could safely grow to its immense size. As vertebrates evolved and began to dominate terrestrial ecosystems later in geological time, the advantage of large size may have diminished as the pressures of predation and competition increased. However, during the Carboniferous, this relative freedom from predation allowed these massive arthropods to thrive. Arthropleura is believed to have been primarily herbivorous, feeding on decaying plant material on the forest floor. The abundance of plant matter during the Carboniferous would have provided an ideal continuous food source. This steady, nutrient-rich diet enabled Arthropleura to grow to such large sizes as their environment supplied both the oxygen and the nutrition necessary to sustain massive body sizes. The Carboniferous period was characterized by a warm, humid, and stable climate. Large, swampy environments dominated many parts of the world, creating a perfect habitat for arthropods like Arthropleura. These swamps and wetlands offered a stable ecosystem with high humidity, which was essential for the survival of large arthropods. Moisture is particularly important for terrestrial arthropods because it helps them avoid desiccation, a serious risk for creatures with exoskeletons. The large surface area of these creatures would have made them more prone to water loss, so the consistently humid environment would have helped them maintain proper hydration. Unlike other arthropods, Arthropleura would have undergone molting, a process known as ecdysis, to grow. Arthropods have a hard exoskeleton that cannot expand, so they must periodically shed this external covering in order to grow larger. Each molt allowed Arthropleura to increase in size, and the abundant resources and high oxygen content of the Carboniferous period likely made this process more efficient, enabling them to grow larger with each molt. Molting is a vulnerable time for arthropods, as their new exoskeleton is soft and leaves them exposed to potential threats. However, given the relatively low predation pressure during the Carboniferous, Arthropleura may have been able to molt without significant risks, contributing to their impressive size over time. Other arthropods, such as giant dragonflies or Meganeura and large scorpions, also achieved massive sizes during this period for similar reasons. This evolutionary success can be attributed to the balance between environmental conditions and the biological capabilities of arthropods at the time. Paleobiology. All fossils of Arthropleura available are believed to be exuviae, molting shells instead of carcasses. The good preservation of its thin exuviae, buttressing plates around the leg base, and evidence of 3 cm deep trackway fossils, namely the Ichnotaxon, Diplecnites, Quithensis, altogether suggests that they had a sturdy exoskeleton and roamed the land. Arthropleura was once thought to have lived mainly in coal forests. However, it probably lived a forest-independent life, as fossils of the trackway were found in more open areas, and fossils were found even after the Carboniferous rainforest collapse. There is no solid evidence for the diet of Arthropleura, as the fossils that were once considered coprolites, including lycopod fragments and pteridophyte spores, are later considered to be merely coexistence of plant fossils and exuviae remains. Nonetheless, the interpretation of a herbivorous diet is still accepted, and it is estimated that Arthropleura ate not only spores but also sporophylls and seeds, based on its enormous size that possibly required ample nutrition. When it comes to Arthropleura's diet, it was also found that Arthropleura had a well-preserved gut region which was packed with plant remains, mainly lycopod fragments such as Lepidodendron. This information helped in concluding that Arthropleura was not only herbivorous, but also possibly omnivorous. The complete head and trunk anatomy of Arthropleura suggested that it was likely a detritivore. Arthropleura did not have the forcipules or postmandibular cephalic limbs of predatory centipedes or arachnids, and its trackways, diplosegmentation, and short millipede-like locomotory limbs imply that it was a slow-moving animal. Through careful observation of Arthropleura's fossils, the likeliest modes of behavior of the Arthropleura were determined. The Arthropleura would invade exposed environments and retreat to levee forests during wet seasons. Thin cuticles on the Arthropleurids indicate that these creatures were exposed to a terrestrial habit. Other prehistoric arthropods. Pulmonoscorpius. Pulmonoscorpius is an extinct genus of scorpion that lived during the Mississippian period, the early Carboniferous, in what is now Scotland. The genus includes a single recognized species, Pulmonoscorpius kirktonensis, which ranks among the largest scorpions ever discovered. The largest known specimen measured over 70 centimeters or 28 inches in length. Unlike modern scorpions, Pulmonoscorpius retained some primitive arthropod traits, such as large lateral eyes and a lack of features suited for burrowing. It was likely an active daytime predator, and the presence of book lungs suggest it was fully terrestrial. Fossils of Pulmonoscorpius kirktonensis were discovered at East Kirkton Quarry in West Lothian, Scotland, in rock layers dating to the Visean and Serpucovian stages of the Mississippian or early Carboniferous, around 336 to 326 billion years ago. The genus name combines Latin pulmonis or lung and Greek scorpios or scorpion, while kirktonensis refers to the quarry. Described in 1994, Pulmonoscorpius is known from 16 complete specimens and over 300 fragments. Only the outer layer of its cuticle is preserved, about 15 to 18 nanometers thick, Fossils are primarily found in finely laminated limestone, which can be dissolved with acid to expose the cuticle. Most specimens are flattened, making three-dimensional reconstruction speculative. The diet of Pulmonoscorpius remains uncertain, but it's likely that it fed on smaller arthropods and possibly small, newly emerging tetrapods. Most fossil specimens measure between 13 and 280 millimeters, or 0.51 to 11.02 inches, though one large fragmentary specimen suggests a length of about 70 centimeters or 28 inches. Only the outer cuticle has been preserved in these fossils. Pulmonoscorpius has a distinctive anatomy, with two pairs of eyes on its prosoma, the head and legs region. This included median eyes near the center and large lateral eyes, each with 40-60 ocelli, a trait shared with more primitive scorpions and other arthropods. The prosoma was protected by a carapace, followed by the mesosoma, which featured 7 segments that became more textured with age. Its tail, or metasoma, had 5 segments, ending in a venomous telson. There may have been sexual dimorphism, with females potentially having broader metasomal segments. A juvenile specimen lacking certain telson features might even represent a separate species. Meganeura. Meganeura was one of the largest flying insects ever to exist. The name translates as large veins, a reference to the network of veins that supported the insect's wings, like a skeleton, and supplied oxygen. Meganeura is an extinct genus of large insects that lived during the Carboniferous period, known as one of the largest flying insects to ever have existed. Its name means large veins, referring to the intricate network of veins that supported its wings and facilitated oxygen flow. Living around 300 million years ago, Meganeura belonged to a group of insects known as griffin flies from the extinct order Meganeura. It likely resembled a modern-day dragonfly with a long, slender body and large prominent eyes. However, Meganeura was far larger, with an estimated wingspan of 25.6 to 28 inches or 65 to 70 centimeters, making it significantly more robust than its contemporary relatives. Its wings, like modern dragonflies, were reinforced by a complex vein structure. The massive size of Meganeura is believed to be linked to the high oxygen levels of the time, with atmospheric oxygen making up 35% of the air, compared to today's 21%. This likely allowed insects to grow much larger than they can today. One of the most notable features of Meganeura were the spines on its large appendages. While their exact function remains uncertain, scientists speculate they may have been used for trapping prey or possibly for mating and anchoring during interactions with other insects. Meganeura was a formidable predator, equipped with large, highly developed eyes and sharp mouthparts for hunting. Its massive eyes gave it excellent vision, allowing it to spot prey easily. Thanks to its enormous size, Meganeura could hunt a wide variety of insects, as well as small amphibians and vertebrates. At the time, amphibians were still adapting to life on land, making them easy targets for this giant insect. Like modern dragonflies, Meganeura likely hovered around streams, ponds, and other water bodies where prey was plentiful. Living millions of years before birds and bats appeared, Meganeura dominated the skies as the top aerial predator of its time. Pterygotus. Pterygotus was a massive predatory eurypterid, an extinct group of aquatic arthropods. In fossils dating from the Middle Silurian to the Late Devonian have been found on 4 continents: Australia, Europe, North America, and South America, suggesting it had a near-global distribution. The genus was first described in 1839 by Swiss naturalist Louis Agassiz, who initially thought the remains were from a giant fish, naming it Pterygotus, meaning winged one. He corrected his mistake 5 years later when he realized it was actually an arthropod. Among the largest eurypterids, Pterygotus species could grow to impressive sizes. The largest, Pterygotus grandidentatus, is estimated to have reached 1.75 meters or 5.7 feet long, while other species like Pterygotus impactus and Pterygotus anglicus were also giants, growing over 1.6 meters or 5.2 to 5.4 feet. Although surpassed by even larger Eurypterids like Arthropleura over 2 meters and Jaekelopterus up to 2.6 meters, Pterygotus still likely weighed around 30 kilograms. Some species, like Pterygotus capaninensis, were much smaller, just 50 centimeters or 20 inches. Armed with powerful chelicoral claws, Pterygotus was a fierce predator. These robust claws allowed it to puncture and grip prey, and its visual acuity, similar to modern predatory arthropods, made it an efficient hunter in ancient seas. Pterygotus had large compound eyes, which provided excellent visual acuity. These eyes were likely well suited for detecting movement in the water, allowing Pterygotus to hunt efficiently. The size and structure of its eyes suggest it had good depth perception and could spot prey from a distance. The prosoma was covered by a hard carapace that protected its vital organs. The body also featured a segmented abdomen, which contributed to the flexibility and maneuverability in the water. This segmentation was typical of Eurypterids and helped them adapt to their predatory lifestyle. While the exact coloration of Pterygotus remains unknown, some scientists speculate that it may have exhibited various patterns or colors for camouflage. This would have been beneficial for ambushing prey or avoiding larger predators in its ecosystem. Jaekelopterus. Jaekelopterus is a genus of predatory Eurypterids, a group of extinct aquatic arthropods. Fossils have been found in early Devonian deposits from the Phrygian and Emsian stages, with 2 known species. The type species, Jaekelopterus rhenaninae, discovered in brackish to fresh water strata in the Rhineland, and Jaekelopterus howellii, found in estuarine strata in Wyoming. The name honors German paleontologist Otto Jaekel. Jaekelopterus rhenaninae is estimated to have reached around 2.3 to 2.6 meters or 7.5 to 8.5 feet, making it the largest arthropod ever discovered, surpassing other large arthropods like Arthropleura, Pterygotus, and the millipede Arthropleura. In contrast, Jaekelopterus howellii was much smaller, at about 80 centimeters or 2.6 feet long. Jaekelopterus shares similarities with other pterygotid Eurypterids, featuring a large expanded telson, the last body segment, and enlarged pincers. Initially classified as species of Pterygotus, they were later recognized as a separate genus due to differences in genital appendages, though this initial distinction has since been revised. Key characteristics include a triangular telson and distinct clawed denticle arrangement. With a powerful chelic array and compound eyes, Jaekelopterus was likely an apex predator in early Denovian Euramerican ecosystems. Despite being dubbed sea scorpions, the fossil evidence suggests it thrived in freshwater environments. The pterygotid Eurypterids, which include some of the largest known members like Pterygotus and Arthropleura, have intrigued scientists for their impressive size. Several factors might explain the remarkable growth of Jaekelopterus, its relatives, and other large Paleozoic invertebrates. These factors include predation, courtship behavior, competition, and access to environmental resources. However, size isn't just about genetics. There are biological limitations that restrict how big arthropods can get. For example, respiration, the energy costs associated with molting, locomotion, and the properties of their exoskeleton all play a role. Interestingly, while the robust claws of pterygotids are heavily sclerotized, most of their preserved body segments are thin and unmineralized. Even the plates that form their abdominal segments, called tergites and sternites, are typically found as very thin compressions. This suggests that pterygotids had a lightweight construction, which may have been crucial for their evolution into giant sizes. In fact, this lightweight build reduces the factors that limit body size, making it easier for these creatures to grow larger. But even though Jaekelopterus and other giant pterygotids are the biggest arthropods out there, they likely weren't the heaviest. Other large Eurypterids, particularly those from the Hibbertopteridae family, like the nearly 2-meter-long Hibertopterus, might have matched or even surpassed the pterygotids in weight. So, when it comes to size, it's not just about length, it's also about how an organism's body is built. Jaekelopterus had an impressive set of eyes that provided it with stereoscopic vision, meaning it could see in 3 dimensions, a trait typical of many predator animals. Interestingly, the structure of its eyes closely resembles those of modern horseshoe crabs. The unique square-like pattern of receptor cells in Jaekelopterus compound eyes is similar, but not identical to that found in horseshoe crabs, indicating a specialized visual system. One standout feature of Jaekelopterus is the size of its photoreceptors. Measuring around 70 micrometers, these receptors are significantly larger than those in humans and most arthropods, which usually range from 1 to 2 micrometers. In fact, they match the size of photoreceptors found in modern horseshoe crabs. The distinctive eyes of horseshoe crabs give them an advantage in low-light conditions, enhancing edge perception and contrast. Since Jaekelopterus had similarly structured eyes, it likely possessed the same adaptations, making it well-suited for its predatory lifestyle. With this advanced vision, Jaekelopterus was a formidable hunter in its aquatic environment.